When you push the beam finder switch, it inserts R4458 in series, which reduces the standing current in the output amplifier, which reduces the scan and provides the beam finder feature of the instrument. Standing current in that output stage, by the way, is 80 mils per side, and signal current is about 8.2 milliamps per division. The trigger selector schematic is pull-out schematic 4. Now we won't discuss the switching logic. We'll refer you instead to the tape on 7000 series display switching, or you might want to refer to the simplified switching diagram on figure 2-20 in the 7704A manual. Now the circuit includes two of the channel switching ICs, the MO36. There's U2404 as the A trigger selector, and U2424 as the B trigger selector. Now the trigger signals come in at the left of the page. The left vertical signal from the left vertical plug-in, of course, by way of the interface pins A13 and B13 into pins 2 and 15 of both of the ICs. The right vertical into pins 7 and 10. Notice the 50 ohm termination appears down by the B trigger input. Now each of these inputs are bases of transistors inside of the ICs, and the emitters are down below, pins 1, 16, 8, and 9. Now pin 1 is related to pin 2, pin 16 is related to pin 15, pin 8 to pin 7, pin 9 to pin 10. Now the command lines come in at pins 4 and 14. Now pin 4 is the switching command signal. That line is under the control of the A trigger source switch. If right trigger source is selected, pin 4 will be high. If left vertical trigger source is selected, it'll be low. If vertical mode is selected on the trigger source switch, and the vertical mode switch has selected right vertical, then it'll be high. Select left vertical and it'll be low. In the alternate mode, it'll alternate between high and low. Now in the chop and added modes, pin 4 will be low and pin 14 high. So when pin 4 is high and pin 14 low, then we pass the right signal. When pin 4 is low, we pass the left signal. When pin 4 is low and pin 14 high, we add both of them. Now the gain of the channel switch and the output amplifier is 1. The signal level is 25 millivolts per division per line. Now off to the right of the page, as it goes into the horizontal plug-ins, it'll be terminated in 50 ohms and has a current signal value of 0.5 mils per division, or across the 50 ohm termination, 25 millivolts per division. Now the output from the ICs, there at pins 12 and 13, are collectors of transistors, and the current generated in the emitter resistors down below flows out through those pins, and the standing current then flows through R2413 and R2414 to plus 15 volts. The signal current passes through the transistors to be terminated in the 50 ohm line in the horizontal plug-ins with that 25 millivolts per division per line that I mentioned a moment ago. Now as we look at the B trigger selector output, we see that it goes two places, one into a grounded base stage, and that becomes the vertical signal out. Now that push-pull signal goes to the signals out board, where it's amplified and appears at the front panel vertical signal jack. Notice that the line is reverse terminated in 50 ohms using R2440 and R2441. Now, in the signal's outboard, there is further 50 ohm termination for the signal. Now, the output from the IC, there at pins 12 and 13, also terminates in 50 ohms using 2431 and the little RE of transistor Q2434, and then of course the same thing on the other side. Now the signal voltage, which appears across that 50 ohm termination, is applied to the bases of Q2444 and Q2446. The signal taken off across collector load resistor R2443 drives the horizontal plug-in. However, the horizontal plug-in, again, is terminated in 50 ohms. So really that is the collector load resistor for this amplifier stage. R2444 is a thermal balance resistor, and C2444 the conventional bypass. Notice that there's some emitter peaking in C2445 to improve the high frequency response. CR2444 and CR2449 keep transistors Q2444 and 2446 from saturating when the B time-based plug-in is not inserted. Now, we wouldn't have the 50 ohm load on those transistors at that time. The transistors would saturate. That would then place a load on the vertical out signal. So those diodes catch the collectors of the transistors at about 600 millivolts above ground to prevent saturation. Horizontal interface is found on pullout schematic 6. Here we take the output from the A and B horizontal plug-ins and select one or the other or neither. And all that's done by a channel switching IC U2320. The output as a push-pull signal then drives into the horizontal amplifier. The entire amplifier has a gain of 1. Now the A horizontal signal comes directly from the plug-in by way of the interface schematic. It comes from A11 and B11 in at pin 2 and 15 of the IC. Notice that the line is terminated in 50 ohms. The signal current is a half mil per division, or 25 millivolts per division per line. So at pin 2, we'll have a positive going 250 millivolt ramp. On pin 15, we'll have a negative going 250 millivolt ramp. Okay, the B signal from the B time-based plug-in, push-pull again, comes in at pins 10 and 7, plus on 10, minus on 7. Now those 4 inputs are bases of transistors within the IC, and their emitters are down below at pins 9, 8, 16, and 1. Now notice the labeling down below there that says A horizontal and B horizontal. That's turned around. B horizontal should be 9 and 8, and A horizontal 1 and 16. Now emitter pin 1 goes with base 2. Emitter 16 goes with base 15. Emitter 8 goes with base 7. Emitter 9 goes with base 10. Notice between emitters 8 and 9, for example, our resistors R2311 in series with the gain adjustment, and that is in parallel with R2315 and RT2315. We'll talk about that in a moment. Now those are the gain determining elements. Now the current generated in those emitter tails flows out through pins 12 and 13. Those are just collectors of NPN transistors. The standing current then flows through R2333 and R2335 to plus 15 volts. The signal current flows through the grounded base amplifiers Q2331 and Q2337, and over on the horizontal amplifier diagram will be terminated in 50 ohms. So if we take half the value of the emitter tying resistors plus the little RE of the transistors inside of the amplifier, and that comes to about 50 ohms, and then, as I said, the terminating resistor in the horizontal amplifier is 50 ohms, and this thing would have a gain of 1. Now, since the beta will be different with different transistors inside of the IC, and there are some losses to the grounded base stage, then you'll find that the value of the emitter tying resistors run just a little bit lower than that calculation calls for. Now, these gain resistors allow one to adjust not only the gain of the amplifier, but the gain balance between the A horizontal and B horizontal inputs. Now, in shunt with the gain determining resistors is the thermistor RT2315, and then of course one over by the other emitters. Now, that's to compensate for some losses in gain within the amplifier as the temperature increases. The thermistor has a negative temperature coefficient, such that as temperature increases, that resistance decreases, thereby increasing the gain of the amplifier. Now, the command signals that determine whether we're going to get A horizontal, B horizontal signal, or neither, comes in at pins 6 and 4. The one in at pin 6 is the vertical horizontal inhibit, which comes from the readout circuit. Now, that'll be high to inhibit, that is, it turns off both A or B horizontal, and the readout information will be injected over in the horizontal amplifier. Pin 4 has the mainframe switch signal called display B command. It comes from the logic circuit. When it's high, we pass the B horizontal. When it's low, we pass the A horizontal. Incidentally, pin 14, which we used in the trigger selection for the add mode, is not connected in this IC, and no connection constitutes a low. Well, since this entire amplifier has a gain of 1, the output would be a signal current of 0.5 mils per division. And since it's terminated in the horizontal amplifier in 50 ohms, then the signal value would be 25 millivolts per division per side. Okay. And our screen voltage is 36 volts. And when the magnifier is on, the newer instruments limit and the positive excursion at about 75 volts, and the negative excursion at about a minus 5 volts. And the earlier instruments would limit at 90 volts and minus 15. We'll talk about the modification that brought about that change a little later. Now for inputs, we have the input ramp. It's push-pull, 25 millivolts per division per side. So for 10 divisions, we'd have 250 millivolts of ramp. Positioning information, of course, is in the plugins. And then there's the X readout information. That goes into a push-pull amplifier composed of Q4321 and Q4331. Its output then drives into left and right operational amplifiers. The left one at the top and the right one at the bottom. All right, let's look right at the input. The lines are terminated in 52 ohms as we drive into the base of that push-pull amplifier. Now the X readout has a value of about 1 volt per division. It provides horizontal positioning as well as the X portion of the readout character generation. Now that 1 volt per division is just too much, so we attenuate it about 18 to 1 using R4300 and R4302. Now those two resistors in parallel provide the 52 ohm line termination for the minus side of the horizontal amplifier signal. Now for the readout information, Q4321 and Q4331 form a paraphase amplifier for the push-pull ramp drive. It's a push-pull amplifier. This amplifier provides a current drive to the right and left operational amplifiers. In the collectors, R4321 and the network on the other side provide thermal balance. C4321 provides the conventional bypass. Now, in between the emitters, we have some more temperature compensation in the network R4313 and the thermistor RT4313. It compensates for a loss in gain at higher temperatures throughout the entire amplifier. As the temperature increases, the resistance of RT4313 decreases, thereby increasing the gain of the amplifier. Now the gain of the left operational amplifier, for example, would be the value of RF, R4329, that's 200 ohms, divided by 1/2 of the parallel combination of whatever's in between the emitters of Q4321 and Q4331. Let's see, R4315 is 100 ohms. Then we have R4313 and the thermistor. And then in parallel with that would be the horizontal gain control and R4311. Well, that parallel combination comes out to about 55 ohms. Half of that then would be 27.5, plus a little RE for Q4321, and that is the RI value to the operational amplifier. Now, RF gets a little complicated, so we'll talk about that later. There's some high frequency peaking in R4312, C4312, and tied right between the emitters is C4315. Notice that the emitter current flows through Q4304. Now the base of that transistor ties over through a section of the beam finder switch to ground. The emitter ties to a minus 15 volts, so that transistor is saturated, and the emitter current then for the push-pull stage flows through that transistor. Now as you push the beam finder, it opens a connection to ground. The base of Q4304 connects to a minus 15 volts. The transistor turns off, and now the emitter current for the push-pull amplifier must flow through R4304, reducing the current through the amplifier and thereby reducing the scan. Notice the centering adjustment. Now that control and resistors R4323 and the one on the other side become RI resistors to the operational amplifier, pumping plus and minus current into the right and left amplifiers to provide centering. Well, let's look at the left amplifier. It's up at the top there. Now there's a low frequency path and a high frequency path. Let's take the low frequency path first. Q4325 is a collector loaded stage. It drives into grounded base amplifier Q4351, which in turn drives into the emitter of grounded base amplifier Q4356. The collector load for that transistor is the constant current supply out of Q4371. Now, all of the current doesn't flow through that transistor. Notice it's bypassed by R4370, so we don't have to have quite as husky a transistor there. But with an active element as a collector load for that output transistor, we can supply the large currents necessary to drive the deflection plate capacitance when that output is going in a positive direction during retrace. Now the feedback path takes off from, well, those common collectors into an attenuator composed of R4374 and the parallel combination of R4382 and R4384. That's a 20-to-1 attenuator. Let's keep that in mind. We pass through emitter follower Q4381 and through RF resistor R4329 to the input to the amplifier there at the base of Q4325. Now we said that we'd talk about the gain of this amplifier. Let's go back to the emitter tying resistors to that input stage. We said that was 55 ohms. Half of that would be 27.5. Let's add a little bit for the little RE and call it 29 ohms. All right, if we take the value of the RF resistor, which is 200 ohms, divide that by 29, multiply it by 20 because of that attenuator we had over there, and we come out with a gain of 140. Well, if we go back to the input with a ramp of 25 millivolts per division per side times 140, we come out with a 3.5 volts per division deflection sensitivity per side. Now, right between the driving amplifier and the output amplifiers is a limiting network composed of CR4323 and down below CR4333, and in between the back-to-back diodes there, CR4340 and 42. Now, the aim of this network is to keep the output transistors from saturating when, with a combination of magnification and positioning, we would drive the beam, say, 2 screen diameters off screen. Now, if the transistors saturate at that point, then there will be recovery problems. Now, in the early instruments, the limiter just didn't work in the negative excursion. And Q4366, you see in the right amplifier, down below there, would saturate. Now that's where the minus 15 volt limit came about. In the upper excursion, Q4371 didn't saturate, but it did get up to 90 volts. Now that was a good enough limit. It was just the negative excursion that caused the problems. So modifications were made to the circuit, we'll talk about the values in a moment, which caused the output to limit at plus 75 volts and minus 5 volts. Well, let's see how the limiter works. Let's go up to the base of Q4325, or rather the cathode of CR4323. We have a positive going ramp there, which is pumping current through that diode and into the feedback network. Or I guess we can say that the collector of Q4321 is trying to raise the cathode of that diode. You see, at that time, Q4321 would be drawing less and less current. Now remember, we're talking about a condition here in which, with the mag on and positioning to such a condition, that CR4323 would just run out of electrons, that's all. And that occurs just before saturation would occur at the output. All right, when that transistor turns off, then CR4340 turns on to retain a load at the output of Q4321. In the opposite excursion, then CR4333 down below would disconnect, and CR4342 would turn on to retain the load on the output from the driver amplifier. Now notice the input transistor to the left operational amplifier is an NPN, and as the ramp is being developed, it's turning on harder. And the input transistor to the right amplifier is a PNP, Q4335, so it turns on harder as the ramp is being generated. Now let's go back up to the left amplifier. Now let's see, we said we were going to turn on Q4325 harder as the ramp was generated, but the grounded base amplifier Q4351 would draw less current as the ramp was being generated. However, we don't have to worry about that. We've got a high frequency path off the collector of Q4325 through C4325 to drive into the emitter of output transistor Q4356. The purpose of Q4351, by the way, is just to provide a DC offset. We could have used a zener there, but a transistor is more accurate. Notice the capacity coupling between the emitter of Q4356 and the emitter of Q4371. Well, if Q4356 begins to turn off, then we'll get some signal voltage at the emitter of that transistor, which in turn would allow us to couple that current up into the emitter of Q4371 and aid in pulling up on the common collector as we drive the deflection plate capacitance. A moment ago I called Q4371 a constant current supply. Now the current through the emitter resistor there is about 8 mils. But as the ramp is generated and the collector of Q4371 moves down, then the additional current comes through bypass resistor R4370. Now the base of Q4371 and the transistor down below there sets at about 78 volts. Now that's a rather large base bypass capacitors off all of those bases in the output amplifiers. We want to make sure that these grounded base amplifiers indeed have grounded bases. Notice the 100 volt supply comes from over in the lower left hand corner, where we take right off the 150 volt supply and drop through a 2.2K value of our 4328. Now we can get by with just a resistor to supply the 100 volts because as the current is increasing in the upper amplifier, it's decreasing in the lower amplifier, and the current through that 2.2K resistor to the 150 volt supply remains constant. Same thing is true with the minus 44 volt supply. This supplies the emitters of Q4356 and down below Q4366. You notice that that is a decoupled minus 50 volt supply, dropping through a 200 ohm resistor to provide the minus 44. That again, since one transistor is increasing current while the other one is decreasing, then the current load on that minus 50 volt supply is constant. Now let's see why we have an emitter follower in that feedback path. Well, it's a matter of supplying enough current for feedback resistor R4329. Now since with the mag on, we have a swing at the deflection plates of about 80 volts or so, that would take some sizable currents through the feedback resistor to handle that. So the current for the feedback resistor then is taken from that emitter follower stage. Now one reason for the attenuator network is so that you divide down the capacitance seen into the base of Q4381 so it doesn't load down the output circuit. Notice that attenuator is compensated. There's a tweak there in C4374 and the one on the other side, C4391. Now they can be adjusted to match the transient response of the two sides. And then in between is C4385, which essentially finishes the compensation of the attenuator. You see, half of that could be considered to be in parallel with R4382 and R4384. Now that's adjusted at the very fastest sweep speed. R4385 provides damping control. Now the right deflection amplifier is almost a mirror image of the left deflection amplifier. But the only thing different there is CR43 60. Now that's a protective diode protecting the base emitter junction of Q4361 in case Q4335 is pulled out of the socket when the instrument is hot. Now the base of Q4361 sets at a minus 5 volts, and the emitter, you see, of that transistor would pull down to a minus 15 volts, thereby damaging that base emitter junction were it not caught with CR4360. Now right between the amplifiers is that thermal balance control and Q4346. Now what we're trying to thermally balance here is the input stage, Q4321 and Q4331. Now the presence of the readout input to the circuit makes thermal balance very critical, more critical than we can design into the instrument without some adjustment. Now, I called your attention earlier to the fact that Q4325 was an NPN and Q4335 was a PNP. Now we could just tie those two emitters together and everything would work, except that the DC levels